Today we are going to look at diagrams. Diagrams is a library that allows you to describe pictures, beautiful pictures in elegant and compositional ways. And to have a concrete goal, we're going to try to visualize the game tree of tic-tac-toe using diagrams in this episode.
So, welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed. We invite you to submit questions or comments in the chat, and we'll try to show them on screen and discuss them.
Yes, so actually this episode connects to the previous episode in which we did compute the game tree of tic-tac-toe, but you don't have to be afraid if you have not watched the previous episode, because we're going to explain all the things that we need in order to do the visualization, and we don't have to repeat most of the actual computing. We are only going to use the data types. The motivation for both the previous and this episode was this XKCD, which I'm showing here again, which has a very nice visualization of the optimal strategy you should follow as either the X player or the O player in the tic-tac-toe game. And so what we're going to try to do is, like, after we've computed essentially a game tree that contains similar information to what we have here, is to write the code using the diagrams package that creates a visualization that looks very much like this one. So diagrams is a package which is developed by Brent Yorgi, and it's big, right? It has a lot of different stuff in it, and we will only scratch the surface today because there are many, many features in this package which we don't actually need. But the general setup is that you have a language, and basically a domain-specific language that allows you to describe pictures and compose them in various ways. And this is part of the elegance, that you can describe many things independently of each other and then compose them. And then you have multiple backends that you can use in order to actually get pictures out. And we're only going to use a single backend today, which is the SVG backend, which is probably one of the most prominent ones by now. So let's switch to code. So to start with, in order to do something with diagrams, you need to import a couple of modules. So I've imported diagrams prelude, which gives you all sorts of useful functions, and I've selected the SVG backend here by basically importing this SVG command line backend. And I've copied in the data types that we used in the previous episode in order to describe tic-tac-toe games. And we are only going to need the data types because we don't really want to compute any values. We're going to take the pre-computed values that we had from last time, but we need to understand these data types again in order to be able to visualize them. So I'll go through that step by step, and we're going to try to create pictures out of them. So perhaps the simplest data type that of all of the ones that are listed here is the player data type, right? So we have two players, which are called X and O, and we'll sooner or later have to draw X's and O's on screen. So let's start with one of these simple things. So let's try to draw an O, and I'll just call this O. And the type of diagrams of any kind of picture is just diagram, and then there is an argument, which is essentially the backend that you have selected. And I can either write SVG here to be very explicit, or I can write B. B is perhaps short for backend, I think, is an abbreviation which is defined by any particular backend. So if you want to later switch between backends, you don't necessarily have to change all your type signatures. So I'll keep this because it's slightly shorter. And in order to draw an O, we can just draw a circle. And fortunately, diagrams offers a function that is called circle. And circle takes the radius. And I'll just pick 0.5 with the idea that the resulting circle will fit into a 1x1 square. And that will become important later on. So now we actually have a diagram. So note that like what we haven't said, right, for example, is where we want to have the circle, or what color the circle has, or like there are lots of things which we have either left implicit or simply not stated at all. Nevertheless,
or the dimension of the size, right? 0.5.
The dimension of the size. Yeah, that's also a good point, right? We have said 0.5, but 0.5 what, right? I mean, it's not so clear. And nevertheless, this is a valid diagram, and we can actually produce a picture out of this. So in order to produce a picture out of this, we have to, one option is to use a predefined function which is called main width. And we can use that as the main program of our program that we want to compile. And main width just takes a diagram as an argument. So we can put the O here. And this is now a complete Haskell program. And we can try to compile it. So let's see. So I can run this through Cabal, compile it, and I'll call it with -- help. And then you see that sort of this main width instruments the main program to get all sorts of options. And so, for example, we can specify what the output file should be called, like, so we could say out.svg, and we can actually specify how large we want the file to be. And so I can say I want sort of the width to be 800 pixels or something like that, right? So, and that generates an out.svg, which is now here. And now I can switch back and look at it, and I have a circle, right? And as long as we only have the circle, it doesn't really matter how large it is, because, right, I mean, it's a circle, right? And we are saying in the end by generating the picture, like how large we actually want it to be. So these sizes that we're using here, they're mainly relevant in relation to other things, right? So they're mostly to be thought of as relative sizes compared to other elements of the same picture. So before we go on, I'll try to set this up now. I've written a little script here that tries to monitor things for changes so that I don't have to do the recompilation all the time. So for example, if I now decide that I want the circle in blue, I can use a construct where I say I want the line color to be blue. And hopefully this will update after a short delay. So, okay. So a common thing to transform diagrams is to use this hash symbol. And this is actually internally just function application. So I could also equivalently have just written this, right?
So it just takes a diagram to another diagram.
It just takes a diagram to another diagram. So all these attributes are just diagram transformers, if you like. And you can also write using the standard reverse function application operator, which is AND. So that also just works, right? But sort of the idiomatic or diagram-specific way is this hashed operator, which is like the ampersand that just has higher priority, actually. So that in some situations, whereas ampersand like dollar has relatively low priority, the hash has higher priority. Sometimes in situations where you use operators to combine diagrams, you have to use fewer parentheses. Okay, so this is a way to draw an O. So let's see if we can also draw an X. So for that, there are multiple options of different degrees of fanciness. But so one way is to basically just start with a point, a two-dimensional point, and say that again we just pick some coordinates. So let's say -0.5. -0.5, and then we turn this point into a path to another point, and then finally we can draw the path. Stroke path. Yeah, sorry. Yeah. It's confusing myself. So that's not a full X, that's just a line. So if I show this, then I'll just get a diagonal line. So now I want to compose this with another line, and so now we get into the situation where we want to combine multiple pictures into another picture. So for example, I can compose this with another path, which is going from -0.5 plus 0.5 to plus 0.5 minus 0.5, and hopefully that'll work. Now, why does it work? Because, I mean, what does it even mean to put two pictures on top of each other if they are somewhere, right? Every diagram in diagrams has what's called an origin, an intrinsic origin, and you can actually show the origin as a sort of like there's a debugging function which allows you to show the origin of a diagram, and then you get it printed as a red dot, and you can see that it's right in the middle here. And whenever you put two diagrams atop of each other, which is what this monoidal composition operator does, they're combined so that the origins coincide. Their origins coincide. So this is relevant, right? So if you get larger diagrams, you have to kind of remember where their origin is. But for this simple path, the origin is in the middle, so in the 0 position, and for this one as well. And it also means that we could, in principle, put the X and the O on top of each other, and they would both be sort of have the same center, right? So if I write X.
So that's also why you chose the minus 0.5 and 0.5 as opposed to, for example, 0 to 1.
Yeah. Yes.
Right. Then they would be slightly off center.
So if I want to draw this one in red, let's say, I can again use line color. Right? And I can apply this to the whole picture, right, which is composed out of multiple sub-pictures. So these, so this is relatively nice. So there are other forms of composition as well. There is not just composition on top of each other. You can also horizontally compose two pictures using this operator. Now the objects get smaller because we are specifying in the output, the thing that is recompiling and watching always, that the whole picture should always be 800 wide, right? So so that is like sort of a constant that we're setting there. If we put them vertically on top of each other, then they become larger again, because again, the width of the whole picture is fixed, right?
Before we move on, there's one question about, just to clarify the origin here. So the origin of a diagram that's specified in terms of explicit coordinates, I guess Tom is talking about X here, is the point 0, 0?
I would have to look up. I mean, I must admit that, I mean, like with diagrams, I'm using this from time to time, but not that often. I think if you do a path construction, it is actually 0, the origin, but I would have to look that up again, and perhaps it's also just the center in some sense, but basically every picture has an origin. Every operation has a clearly defined way in which it treats the origin. And you just have to always remember where the origin of your picture is. And if you forget, you can use show origin to show you. But I mean, it is relevant. Okay, so we can, once we have the X and the O, we can define a function draw player that actually takes a value of type player and turns it into a diagram, and that has the obvious definition. So if we get the player X, we use the X, if we get the player O, we use the O diagram. And this is what we are going to do now for all the other data types as well, right? We are going to describe functions that turn values of these data types into diagrams. And we can basically almost always do this directly. And this also is, again, sort of a demonstration of sort of the compositionality that you get, that you can really independently describe how different concepts translate into diagrams, and that you have the language that composes them. Right. So let's look at the other three data types in this upper list, right? So the main idea is that the grid in tic-tac-toe has 9 positions. And in order to visualize these 9 positions, or to represent these 9 positions, we basically have a data type 3, which captures a row of 3 positions. And then we say that a grid is actually 3 of 3 positions of some type A. And so the normal thing that the grid will hold is items. And an item is either empty if, that grid position is not yet taken by a move, or a player has made a move in that position, and then we store which player has made that move. So we want to be able to draw an item next, perhaps. So that is the next step. That is the only interesting case is the one for empty. Because for a player, we just call draw player, right? And what do we do for empty? Now, we could just use the empty diagram, but the empty diagram has sort of no size, and because we want to put things next to each other, and we want to actually take up like an empty space, also some space, right? If you have a row where there is an X and then empty and then another X, we don't want the 2 X's to end up right next to each other. We want there actually to be a gap in there. Mm-hmm. And for that reason, we want to basically create an empty picture of size 1 by 1, and we can use that strut function in order to do that. Okay.
Which does have its origin at 0, 0.
Yes. Well, which does have its origin in the middle.
It's local 0, 0.
Yeah, local 0. Yeah, there is no.
Yeah, fair enough.
Yeah. And now we can look at grid. Draw a grid. And so the reason we chose this 3 by 3 type last time is because it's relatively precise, and it does not allow us to represent any incorrect grids and so on and so forth. But like if we want to put multiple things horizontally next to each other, we can either fold with this bar combinator, or we can use a function which is called hcat, which basically just horizontally concatenates a list of diagrams. So basically we want to turn the rows into lists and the
columns.
The column, no, not really the columns either. So the 3 rows as a whole the outer thing should also be a list, right? And so basically we want a quick function that allows us to, and this should be, well, we'll talk about this in a moment, what should be the argument here. But we want something that goes from a grid of A to a list of A.
Yeah, so the inner list contains elements from a particular row, and the outer list contains every row.
Mm-hmm. Yeah, exactly. And so, now let me just keep this as an A for the time being so that I get HLS back. And so now the items that we have, they are 3 by 3, like a 3 of 3, and 3 is an instance of foldable, so we can basically fmap toList over 3 in order to get 3 of lists of A, and then we can call toList on the outer 3 afterwards to get a list of lists. So that is basically just using the foldable structure that we already have.
Foldable.
And yeah, exactly. And so for the grid, what we can of course try to sort of like parameterize this, or we can write a function that only can draw grids of items, or we can simply also use the fact that grids are functors and say, well, we only really have to concern ourselves with the case if we already have a grid of diagrams, and then we can always fmap over the grid in order to draw the inner things. Okay, so let's see how that goes. Drawing the grid. We have to, well, basically we have to call two lists of lists of the grid. Then we have a list of A's.
A list of diagrams, in fact.
List of diagrams, sorry, yeah. Two list of lists. Okay. So now we have a list of diagrams, and we basically want to fmap hcat over the inner list, and then we want to vcat vertically concatenate the outer.
Yeah, so the outer ones, the rows, are stacked like this. So we do vcat for them, and then on every inner row, they're stacked like next to each other this way, and so we use hcat to do that.
Exactly, yeah. And now we should be able to draw the example grid. So in order to draw the example grid, we have to map draw item over the example grid, and then call draw grid. And hopefully that'll work. Yeah, okay. So we can see here that it's not so nice that we don't have any space between these. So there is a variant of hcat, which gives a little space. So we can use hzep for separator. And here we have to put something in, and that is in relation to this size 1, right? So if we want perhaps 0.05 or something along those lines, and probably here we want vzep of 0.05 as well, and then we get a little bit more space, right? And actually, perhaps we want to have something on the border as well. So and there is a function frame which adds a little white space on every side as well. Okay, so that's our grid. Now, the next step is to draw the game tree. Right. So how do we draw the game tree, or how did the game tree even look like? So the game tree looked like that. We have nodes in the tree, and in every node we stored the player whose turn it was. We stored the current state of the grid. We stored some evaluation for like computing the optimal tree later on. And we store whether this is a winning position. And in this case, this either is storing the winning player, right? Or we store a grid of subsequent moves. And this was already inspired by sort of the goal picture, right? Because the idea is that we are making a move, basically this, if I zoom in, this is basically telling us we should be making this move, right? And then we are looking up in the grid which move the opponent makes, right? And the observation is that this is sort of a nice property that is being used in this picture, is that the moves directly correspond to the grid positions. And therefore, we're using a grid to represent all the next states. And the next states are given by the next type, because in every position we can either have a situation such as we can see here in the upper left corner that we've already played there, and then we cannot make that move again, so then we store that, or we actually store another game tree, which is basically the thing that we are then visualizing recursively in these positions. So that's the goal. So let's try to write this. So let's try to write, let's go back to this one, draw tree. So if we have a tree of, oh no, it doesn't take any arguments. We want to go to a diagram B. And we basically have to distinguish two situations. So we get the player, we get the grid, we get the score, but we don't need it. And if we have a left and a winning player, then we basically just want to draw this grid. That's the grid that is the final state. So we draw the grid. And just as we've already seen that we can do this, we use draw item to draw all the items. Okay. The other situation is that I think in this case we don't even need the grid. That we have children, and the children are themselves a grid, so we can use draw grid again over the children, but now we have to have a function that draws this next tree, right? So we need to have a draw next, which again, if we have a next of a diagram, let's just assume that we have a diagram here as well. Mm-hmm. We can turn that into a diagram. Sorry?
Makes sense. Yeah.
Did you say something? So here we then want to call draw next after fmap of what is it? Draw tree, right? Recursive invocation of draw tree. And this is all very straightforward, right? Which is the point, essentially, right? I mean, so this is really simple. And then in the next case we have either what are our constructors already played, which means we can call draw player P, or we have next of a diagram, in which case we do D. Okay? Mm-hmm. And now we can hope that this is already it, but we have made one mistake, which we'll discover the moment we try to show this. So we need a tree, but we have computed sort of basically the tree that is corresponding to this situation, which is the tree for X. We have computed that last time already. So I can try this with draw tree of X tree, which is coming from the tic-tac-toe module, and see what happens now. And now we see something which looks weird, right? and
nice abstract art.
Yeah, the observation is that like all circles and all x's have the same size. And if we think about it, that's right, because we are never actually rescaling, right? So we were originally in draw grid. We were composing only x's and o's and empties, which we carefully chose to all have the same size. But now we're also composing it with entire grids, which don't have the same size. Draw grid produces something which can have a different size. And in order to make draw grid produce something that also has the same size, always, right? Let's just rescale it here. And in order to rescale it, we're actually going to center it first, because the horizontal and vertical composition does not mean that the origin ends up in the center. There are different rules for that, but there is a function called center xy that is just centering this. I'm not sure whether this changes the output somewhat, but not. It does not fix the problem. The real fix of the problem is that we want to scale the whole thing so that it is of 1x1 size again. And because it is supposedly square, we can do a uniform scale and just say that the x dimension should afterwards be 1. And hopefully this will do it, right?
That looks a lot more reasonable.
Yeah, that looks very much like the thing that we want, right? So perhaps you can argue that the line width is a little bit thick. So if you want, we can do the line width, set that to very thin on the very outside. And actually one of the interesting things about the line width is, which is a good thing, is that it is not being scaled, right? So even though we are scaling the individual pictures, the line width, even of the small images, if we zoom in here, is still the same. If you really want that, you can change that. But diagrams has this notion of widths which like are either local or global and are subject to scaling or not, depending on whether you want that. Okay, so I'm noting that we are already basically at the end of time, so I'm not quite sure. So there's a couple of comments I should probably make. This is, first of all, this is not exactly the same picture as we're seeing here. And that is because simply we haven't computed the same tree. And but we could, right? We could change the computation of the tree. So this is still a correct tree, but the one that XKCD uses is a little bit nicer because we have been just doing some sort of naive optimal strategy, but we are not always taking sort of the shortest path to a victory. And there are other heuristics you can possibly apply. Like if you are playing a draw in best play, then are there situations in which the opponent has more opportunity to make mistakes or fewer? And so by taking these kinds of heuristics into account, and then there are symmetries, right? I mean, it doesn't really matter whether we play here or in the upper left corner because the board is entirely symmetric. So so if you take all these things into account, you can tweak it to get the other thing. There are some other things which can be done in order to make this look nicer or even better, right? So for example, this diagram highlights always sort of the latest move, which makes the whole picture a little bit easier to navigate, right? We could be doing something similar. And leaves of the tree, winning positions, are being highlighted. And perhaps that is the one minor change that I should still show, and or I don't want to go too much over time, to see that if something is a winning position for red, and for simplicity, because drawing the line and identifying where the line has to be drawn, like in the original picture, would actually be a little bit more complicated. I'll just frame the picture and give it a red background, because X, a red background for if X wins, but in the picture for X there are only winning positions for X. So what we can do is we can say if we have a winning position here, we can just compose this with a draw win of the winning player. And then I need to define draw win, which is player to diagram B. And basically here I want to use a square, a 1x1 square, which has a line color of, actually of the player color. So let's call that player color. And a line width of 0. Not of 0, let's say of ultra thin. And a background color of the player color, but not the player, the player color is red in this case, so if we make the background solid red, then it would be quite dominating. So let's make it, so there is a function called blend that you can use to mix colors. So let's mix white with the player color to quite some extent so that it gets much lighter. And we still need to define player color. And player color of X is going to still be red, and player color of O is going to be blue. And let's see if that updates. Yeah, so now we can see that like there are really no winning positions for blue. I think that's relatively easy to see, right? If X starts and with best play, then blue has no chance. And actually, almost everything actually leads to a win for red. The only situations where red does not eventually win, and yeah, for the small boards, this is hard to see whether they still have a red frame and a red background, but you can see here in the middle grid, there are 2 positions which actually lead to draws, and these are the only 2 draws in the game tree for X. Yes, so as I said, I mean, there would be other interesting changes we could still do, but I think we are out of time, and perhaps we have questions. I don't know. Do we have?
No, there's just some chat about that this kind of thing could be a long road. Like, you know, you could spend hours and hours perfecting this. Which is certainly possible.
Yeah, I mean, you can do something like how exactly do you want to treat the corners, or do you want to make them slightly smaller? But the point is, even if you do that, it is still local changes, right?
Yes.
I mean, you're
Yes.
it's all just abstract things. But yeah, perhaps I should briefly show the tree for O as well, which looks more complicated because it's the second player and it's also an unoptimized tree. So it takes also a little bit longer to compute. Or did my auto update break in the last moment? Yeah, here we go.
Here it is.
So here you can see that the games tend to take longer, right? Because X makes the first move, and then O has to react. So that's why there are more smaller grids on the board. But now it's still like a draw with best play, and there are many more situations which lead to draws. There are also situations where X plays stupidly, so to say, and then blue wins. But in this grid, there are no situations where red wins, or where X wins. Yeah.
There's maybe one final question, which is sort of a more broad question: whether we use this for anything in our daily work. Maybe I can give one example of this.
Yeah, sure.
So back a few years ago, we did some analysis for a client of some performance problems that they had in their server, and we wrote a tool called GHE Events Analyze, which takes an event log, which has profiling information from it and generates some pictures from it, which was very helpful for finding where the problems was, and diagrams is the perfect thing for that sort of thing. So yeah, just one example. Like I've used this many times for all kinds of things for professional work.
Yeah, I've also used it. I mean, not all the time, not in my daily work, I would say, but it is a useful tool to come back to over and over again. And I think it is really nice. It is really nicely designed. I think,
yes,
if anything, the only slight drawback is that it is using a lot of overloading, and the intent is clear that like many things are just composable with each other without explicitly calling conversion functions. But as is often the case with overloading, is if you make things very overloaded, it's a little bit harder to discover what even the intent is, or what like sort of the general meaning is. So which is why I actually like to write explicit type signatures even for all my diagrams, so that I don't run into overloading errors quite that often. But yeah, so but generally I really like it. So yeah. Okay.
All right. Thanks everyone for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe, and feel free to leave any comments below the video. We'll leave the chat open for a few more minutes if there's any more questions today. And then we'll probably see you again. We haven't discussed the date yet, but I suspect in 2 weeks.
Okay. Bye-bye.